For computational tools for economics and management. The topic for today is optimization, and I would like to give you some general ideas about optimization. Then I will use a gravitational metaphor to explain how the standard optimization algorithm is working. And in particular, we will have to explain why using a function of two variables x and y is useful to do something, but in order to optimize it, we then have to slightly change the definition of the function, and we will use f of x, where x is a vector with two components, for example x1 or x2, or as they are often called x and y. We will then use optim, which is the all-purpose optimization algorithm that you will find in R, and see together some simple example. I will keep for a separate video, for a separate segment, the analysis of more involved examples. So let me start with some basic ideas about optimization, which I think can be a useful framework to understand problems. So optimization can really shape the way you think about a problem, and very often you take poor decisions because the problem is poorly understood. And indeed, clear decisions are based on clear ideas, and I have three main suggestions. So the first question you may try to answer is, what is your target, what you are really interested in? This boils down in the optimization jargon to explain clearly what is your objective function. You have something you want to maximize or minimize, and this should be very clear in your mind. As a second step for an optimization problem, you may ask yourself which are the variables that you do control, which are the variables you have control over in your situations. So basically this is tantamount to ask yourself what can you modify, and the variables that can be changed by you are called decision variables. So you may try to think to what you can really do. For example, very often you may have a problem which is involving, say, two divisions in a firm. Well, clearly, you can maybe change the way your division is working, but of course you don't have any control typically on the decision variables of another unit. And this is indeed clarifying what you can do and what cannot be done. Finally, very often you are subject to limitations and restrictions. For example, you may clearly optimize something if you have unlimited budget, but often you have strict budget constraints, and hence your decisions are somewhat restricted and indeed constraints. So the third ingredient of a good optimization problem solver is to think about the constraints you have to face when trying to solve one problem. So a gravitational metaphor is possibly very useful to get the kind of intuition for optimization. So we think right now to minimization problems pretty much because the intuition is easier to grab, but of course nothing is really changing if you think about maximization. Thinking, however, about minimization can help you in using this metaphor. So you can think that minimizing a function is like finding the lowest point on a graph if you follow the force of gravity. So imagine for a second that you have such a graph and that you put a ball and that you start your optimization process here. Of course, this ball is going to fall down using this gravitational metaphor, and pretty much it is going to roll down, and possibly it is going to end up close to the minimizer, which is exactly the point that you are looking for. So you can think, for example, to use another starting point. If I show the point on which I am clicking right now, this is another starting point, but pretty much the story is going to be the same. Gravity is going to bring down your ball, and you are pretty much ending up in something which may be very good approximation of the minimizer. Having said so, this is a sort of easy problem because this gravitational metaphor is working very well, starting from any initial condition, which is from any initial ball. And the problems such as this one are called convex, and usually they are quite simple to solve. But clearly, there are problems which can be much more difficult. I was depicting one of these problems here. This is more difficult for two reasons. The first is that, well, you can start from any ball and the ball is rolling down. This is improving your effort to minimize the function, but of course you end up in a situation, for example here, which is far from the global minimum, which is here. And so pretty much the gravitational metaphor is pointing out that there are more difficult functions to minimize. More importantly, clearly on such a problem, the solution you will find thinking to this gravitational metaphor is strongly depending on your initial starting point. If you place, for example, your ball here, here, you are going to roll down and you will reach this point. But clearly, this point is going to be completely different from the solution that you would have got, starting there. And you may think that this is a sort of, that this description is suitable for one-dimensional function, but clearly this holds in higher dimension. So here you see a surface, assume that you want to find the minimizer. You can place a ball, say, here, or here, or here. Any ball pretty much is meaning a different starting point, and your ball is going to roll down to reach the unique global minimizer that you see here. But there are surfaces that are much more complex and problems that are much more difficult to solve. For example, here you have plenty of local minimizers, and if you put a ball here, you are going to roll down to reach the closest local minimizer, and of course this is possibly going to be very far from the true optimum, which is very far from the point that would be achieved starting from any initial point. So this is again stressing the idea that in order to properly minimize a function, you will have to take some care to start from an initial point which is well chosen in order to find a good minimizer. Now, this is an important technical issue when you want to use R to solve minimization problems. Typically, we write functions of two variables as function of x and y, or if you wish, you can also pretty much write the same function as a function of two variables, which are sometimes called x1 and x2. And of course, both expressions are exactly equivalent. Notice that formally the function here is a function of two variables, but in R we have to rewrite the definition of the function, formally thinking that the function is a function of a unique object, a unique vectorial variable that I was writing here as boldface x, which is indeed a vector. So you can think that the same function is a function of one vector which has two components. And an example is going to clarify what I mean. So you can think, say, to a simple quadratic function like this one. This is written in the familiar notation using x and y. And so f of xy is indeed x squared plus y squared plus x times y plus y. Of course, I can think that this is indeed the same as writing f of x1 and x2, and this is going to be x1 squared, this is going to be x2 squared, this is going to be x1 times x2 plus x2. So basically I am writing x1 instead of x and x2 instead of y. In R, you are using such a representation, you are defining a function of a unique vectorial variable, which is x, and indeed you explain, you compute the value of the function using the components of that vector. So you define f of x in which boldface x is indeed a vector with two components. And this sort of definition is indeed needed if you want to use the all-purpose optimization function in R, which is called optim. So what should you do when minimizing a function in R? So you have to define f as a function of one vectorial variable, and you have to provide an initial starting point. I call the initial starting point here AB, and you can think that this is exactly the position of the ball in the previous graph. And the syntax for optim is the following. You can see that here. You must type optim, then you must write an initial point, in this case AB. Of course, you are using the C operator, which is concatenating the A and the B, which can be thought of as the components of the vector, which is the initial starting point, and then you have to provide the name of the function to be minimized. So let me solve the problem that we were briefly sketching before. I am first defining my function in the very standard and intuitive way using the variables x and y. So f is a function of two variables, x and y, taking as a value x squared plus y squared plus x times y plus y. And this definition here can be used, for example, as we have seen together, to draw heat maps or contour plots. However, this is not the definition which is going to be used by optim. As I told you before, you must define something in terms of a unique vectorial variable x. So you will generally define another function which I called fb. This is just the b version of the function f which was defined previously. This is a function of a unique vectorial object x with two components. Hence, the first component x1 is going to play the role of x, and the second component x2 is going to play the role of y. And in doing so, of course, you have that fb of x is the first component squared plus the second component squared plus the first component here times the second component x1 times x2 plus the second component, which is the y. And now that I have defined my function fb, I should provide an initial point, which is the starting condition for my minimization algorithm. Assume that we have plotted a graph. That's not something I'm going to do right now because it will come in the next slide. And anyway, assume that we have decided to use as an initial condition the point 1, 1. I am now ready to issue the command, which is optim, starting from the point 1, 1, the function fb, as you see here. And if you do that, you will get the following. You will get the following solution. You will get a couple of parameters. Those are the decision variables. So this is the point minimizing your function. So your function will be minimized at x1 roughly equal here to 1/3 and x2 roughly equal to -2/3. At this point here, your function is going to take this value, so this is -1/3, and down here we have more technical information. I will say very soon something about convergence. So to sum up, in order to minimize a function, you have to define the function again. It must be a function of one vectorial variable x, and then you have to pick a reasonable and good initial starting point for the optimization problem. So let me provide you with another example, and in particular This is helping me to show what you have to type when you maximize a function. So to maximize a function, you have to use a special option, and the option, what you have to type is control is equal to a list in which fn scale takes the value -1. And please notice that a bracket is missing there, and so there is a typo on the slide, there is a bracket missing. So why do we want to do so? Well, basically here you want to reverse the so-called function scale. So basically you are multiplying the function by -1, and in so doing, instead of minimizing a function, you minimize the negative of the function, which is equivalent to maximizing. So here I am using, as an example, another function of two variables. So I am defining g is a function of x and y. This is negative x squared less y squared plus s times y plus y. Again, this is a useful definition for the function, because in a second I will have to draw a graph of this function in order to pick a proper initial condition. But as you know, I have to define a second version of the function in order to use the optim command. This is called gb. This is a function of a unique vectorial object, and here I am using a sort of nice trick. So instead of retyping everything in terms of x1 and x2, I am just using the previous definition, which was in terms which was given in terms of two variables. And here I am saying that gb at the point x is just the previous g, in which x is the first component of the vector x, and y that you see here is the second component of the value x. And this is very often handy because you avoid typing a lot and the possible typos. So here, as you see, I have both defined the g and the gb. So the g is going to be used to draw a contour plot. So I am defining a sequence of values for x. Here I am defining a sequence of values for y. I am computing the z for the g function. As you know, we can do that using the outer function. So gz is basically outer of x, y using the function g, and I am hence ready to plot a contour plot. So if you now look at the graph that you see here and you read the levels, you see that pretty much the maximizer should be in the center of this ellipsis here, and so roughly speaking it may be close to 1, 1, something like that. So I have a good starting point because I was inspecting a graph, and I am ready to give the command to maximize this function. So if you type optim starting from the point 1, 1, which was indeed derived from the previous graph, I was looking at a graph and I was guessing that 1, 1 was a reasonable starting point for my maximization procedure. So start from 1, 1, maximize the function gb that you see here, using the option that is needed to maximize instead of minimizing, which is the default behavior. So I am typing comma, control is a list in which one parameter, which is the scale of the function, turns negative. If you type that, you get the following output, which I would like to comment. As you see, R is again finding a minimizer. This time it is a vector, it is a point. The first component, x, also called x1, is 1/3. The second component, x2, which is often called the y, is 2/3. At this point, the value of your function is going to be 1/3. And here you see some additional technical information. Let me briefly comment that. You have the number of functions evaluations and the number of the, let me say, the partial derivatives evaluation. In this case, the maximization algorithm was just computing values of the function, and you could get the maximizer that you see here through the computations of 111 values for the function. More importantly, maybe here you have something which is related to the convergence of the process of the maximizing algorithm. And indeed, 0 is telling you that everything was fine. So 0 is a code to tell you that the maximization algorithm was successful according to R. So the important thing to remember here is that if you see something else here, well, maybe this is pointing out that R was having a difficult time in maximizing or minimizing the function, and hence you should double check your results. This is the end of this segment for the flipped lecture. You will also find another short flipped in which I am maybe exploring a couple of more complex examples. Thank you for your attention.